can we calculate the speed using the graph? Like here, I have here distance time graph. Can we calculate the speed from this graph? Yes, of course, we can. Why? Because the speed is a relation between distance and time. It equals distance divided by time. So if we divide this distance by this time, we can get the speed. But how can we divide it in the graph? Distance is on y-axis, as you remember. Time is on x-axis. To get the speed here, we have to divide distance by time. Distance is y, time is x. This means we are dividing y by x. This means we are getting the gradient. So the gradient here equals the speed. The gradient equals the speed. So we can get the gradient of this graph to get the speed. Good. But which part of this line we can use to get the gradient? Look here, we have distance, we have time. It is a straight line. This means we have a constant speed here. So the speed does not change during this time. What does this mean? This means we can choose any 2 points and we can get the speed in this graph. Because we have here a straight line, this means the speed is constant. This means we can use any part of the line to get the speed. For example, if I choose this point, for example, here, I will get the gradient. You know how to get the gradient? The gradient equals rise, excellent, over run. Okay, where is the rise here? The rise is this line, which is vertical. It is from where to where? It is from 0 to 6. The rise, the gradient, as you know, equals rise over run. The rise is from 0 to 6, so we get the rise by subtracting these two values. Over, the run is from 0 to 3. Look at this, from 0 to 6, this is the rise. From 0 to 3, this is the run. So it is 3 minus 0. Get the final minus the initial here. So the gradient equals 6 over 3 equals 2. The distance is in meters. The time is in seconds. So it is 2 meters per second. Is it the same anywhere? Of course, yes. Look here. If we use these two values, for example, here, from this point and this point, look at this, only this. This is the rise, and this is the run. Look here. This rises from where to where? From 8 to 10. So it equals 10 minus 8 over. This run is from where to where? From 4 to 5. From 4, the initial, to 5. So it is 5 minus 4 equals 10 minus 8 is 2 over 5 minus 4 is 1. So the gradient equals 2 meter per second. The gradient, as we said, it is the speed here. So the speed equals 2 meters per second. We have here a clearer one. The gradient equals rise over the run. Okay, the rise is the change in y-axis, or the change in the speed, or the distance, or the distance traveled divided by the run, which is the time taken to travel this distance. Okay, try to get this one again. I think we can get this. For example, here, can you calculate the speed in AB, in segment AB? Of course, yes. Look at this, rise over run. The rise is from 0 to 3, and the run is from 0 to 3. So it is 3 minus 0 over 3 minus 0. So the speed here equals 1 meter per second. In this one, we'll change the color. In this one here, it is also rise over run. The rise is from 3 to 4. So it is 4 minus 3 over. The run is from 3 to 5. So it is 5 minus 3. It equals 3. 4 minus 3 is 1 over 5 minus 3 is 2. So it is half meter per second. What about CD? This is the run. Where is the rise? No rise. This means the rise is 0 divided by the run. So the speed here equals 0. So it is at rest or stationary object. Here in DE, the rise over the run. This is the rise, and this is the run. The rise is from 4 to 6. So it is 6 minus 4 over. The run is from 8 to 9, so it is 9 minus 8. So 6 minus 2 minus 4 is 2 over 9 minus 8 is 1. So the speed here equals 2 meter per second. In which segment the object is stationary? In CD. In which segment the object is the fastest? In DE. In which segment the speed is the lowest? In BC. Now it is, I think it is clearer. Look here again. Can you calculate this distance? Please, if you calculate it, please